And welcome to SanfordFlipMath. This is PreCalculus. This is our second installment on the section 2.4 from the Demana, Waits, Foley, Kennedy PreCalculus Functions and Graphs book, fourth or fifth edition, since we have a blend of both. In this section we need to talk about the remainder theorem, the factor theorem, transformations on 1 over x, and also solving polynomials with division. Now this is actually quite a bit. So buckle up. I want to hit the remainder theorem and the factor theorem first because those go real quick. And the remainder theorem basically says something like this. If you take some polynomial and divide it by some factor like, well, not necessarily a factor, but by some linear expression like x minus c, it turns out the remainder will be equal to p of whatever that c value is. Okay, now your book says something similar to this, and now the question is, okay, what does that really mean? Okay, so here we go. Let's say I have something like 3x to the third minus 4x squared plus 5x minus 7, and let's say I was going to divide by x minus 2. And let's say I really don't care about the quotient. All I really want to know is what is the remainder. That's my goal. I don't care about the actual quotient. Now, I'm going to take just a second and show you one way to approach this, but this is really not what we're going to end up doing. And so I'm just doing a little synthetic division here. I have all terms present, counting down from third degree, second degree, first degree, etc. And so I'll do a little synthetic. So 3 times 2 is 6. Add. So again, we're just multiplying and adding. Multiply and add. Okay. So the remainder equals 11. Okay. Well, what the remainder theorem says is, if I want to know just the remainder, I can actually take this value and just put it in for x. And my answer should actually be the remainder. So in other words, okay, so here's me doing the p of c, or in this case, the p of 2, that opposite value, that value that would have gone in the box. Okay, so here we go. So it's just 3 times something cubed minus 4 times something squared plus 5 times something minus 7. Okay, like my use of the verbiage here. And that something is just 2. Okay, so whatever would have gone in the box, that opposite. Well, 2 to the third is 8, times 3 is 24. 2 squared is 4, times 4 is 16, plus 10 minus 7. Okay, so this is 18 minus 7, which is 11. And shockingly enough, this is what we got for remainder here. And then, according to the remainder theorem, this should be the same thing, and lo and behold, it is. Okay, so one of the things to see is it's really not that big of a deal when the division is easy, but what if the division is not so easy? So I have x to the 101st power minus 3 times x to the 50th plus 1 divided by, oh, let's say x plus 1. Okay. And again, all I want to know is the remainder. And again, there are times when that's all we want to know. Okay. So if I want just the remainder, then I can do p of, well, the thing that would go in the box would be -1. This is the p of x here, the polynomial that we're dividing into. So here we go. I'm just going to say something to the 101st power minus 3 times something to the 50th power plus 1. I'm just going to substitute in this -1. So here we go, -1 and -1. -1 to an odd power is going to be -1. Well, this is -1 to an even power, so that's going to be 3 times 1 plus 1, so that's -4 plus 1 is -3. And so I just found the remainder of that division without actually dividing. And sometimes that's how it's going to read on the test or a quiz. It's going to say, without dividing, find the remainder if x to the 101st power minus 3x to the 50th plus 1 is divided by x plus 1. And the idea is you're just supposed to substitute in. Okay? All right, one little add-on to this. If something is a factor, when you divide, what should the remainder be? Well, it should be 0. Well, that's what the factor theorem says. So the factor theorem says if you divide some polynomial by some factor, some binomial, you divide by something, and the remainder equals 0, then that x minus c, whatever it was, is a factor. Okay, so just to look at the last couple that we just did, well, the remainder here is not 0. So that means x plus 1 is not a factor of x to the 101 minus 3x to the 50 plus 1. Okay? And in the same vein, since the remainder here was 11, then x minus 2 was not a factor of that big ugly cubic. Okay? All right, so that's all I'm going to say about remainder theorem and factor theorem right now. Yes, there will be a question or two here and there on the test, but time is an issue. Okay, so if you have other questions about that, we can do that in class. Okay, all right, next up, transformations on 1 over x. So what we're saying is we have this parent function, y equals 1 over x. This is the parent function. This is what your book calls the basic function. Okay, and we want to know what happens to it if we do something like, let's say, 3 over x minus 2 plus 1. And this is really a throwback to what we did in section 1.5 with all the transformation stuff. So we could talk about translations and slides and stretches, shifts, whatever. Okay, so we're going to key in on some issues. Okay, now first of all, because of where the x is, the denominator is what I like to refer to as the inside of the function. Okay, so the denominator is the inside. Okay, so for instance, this x minus 2 is inside. Now the question then becomes, what about this 3? Where's that? I mean, because the x isn't inside, so it's not inside. I guess it has to be outside. And I think what I'd like to do is rewrite this in a form that makes it a little more obvious. Now the only reason I'm doing this is because this becomes very, very obvious that this 3 is on the outside. It is connected by multiplication, and if it's connected by multiplication, then it has to be a vertical stretch or shrink. Outside, vertical, do what it says. So this is multiplying the y's by 3. If that's true, it's making them bigger. So this is a vertical stretch of 3. Okay. Well, this x minus 2 is inside, so we're going to do inverse. It's connected by addition or subtraction, so it is a shift. It shifts right 2. Okay, and then this plus 1 is on the outside, so this is vertical, shift, and it is up 1. Now this equation pretty much started out in the right form already. So that's kind of cool. It makes it very much easier. Okay. Okay. So let's do another one. Okay. Now the next one that I'm going to do, it's not going to start in the correct form. Okay. So here we go. This is a different function, and it looks a little different than what we had because it's in a different form. Now you may recall things like horizontal asymptote would be x equals -1, vertical asymptote y equals 2x over x2, etc. Okay, not such a big deal. It's not our purpose right here, but it's related to this. What we're going to do is change it to that form, and we do that by dividing. So this is the same thing as 2x plus 1 divided by x plus 1. Now, x times what is 2x? That's 2 multiply, and then we'll do a little subtraction. So that's gone. This is -1. And so we would write this 2 plus -1 over x plus 1. Well, this is a new way to write y. This whole thing is equal to this. I've done that division. So what we're going to do is write y equals, and I'm going to rearrange this a little bit so it looks more like what we had just a minute ago. Okay, so here we go. There is multiplication going on the outside. So since it's on the outside, it's about y. So it's not a stretch or a shrink this time because it just makes things the opposite sign. Well, if y values go from positive to negative or negative to positive, there is a reflection over the x-axis. And there was a shift, again, inside inverse, left 1, and also up 2. Okay, so that's what happened to the parent function, y equals 1 over x, to become this equation, or this equation, because they're both the same equation. Okay? All right, and then the last thing we're going to talk about is solving polynomials with division. Now this is really probably the most important or the biggest deal in this section. And so what we're going to do is try and find zeros. Okay, so here's an example of what we'd like to do. We want to find all of the zeros. Okay, so we're going to find all of the zeros. Now remember, the zeros are the x values that make y equal 0. So in other words, I want to solve this equals 0. Okay. Now here's the thing. If I could just factor this, then I'd be able to set each factor equal to 0. I have the zero product property, so just like when we solve quadratics, if I can factor it, I can set each factor equal to 0 and then solve each factor. Well, factoring a cubic is sometimes it's a real job. Okay, so what we're going to do that is do a little division. So we're going to take this whole polynomial and we're going to divide it by one of its factors. The problem is, what is that factor? All right, so the way we're going to do this is we're going to find a factor by looking at its graph. Okay, so let's pop over here. Okay, ta-da. So I just typed in the equation, and what we're going to do is try and find one of the zeros. Okay, so here, let me give you the bigger screen. Okay, now as I'm looking at this graph, it looks like this is somewhere between, I think this is a standard screen, somewhere between -1 and 0, somewhere between 2 and 3. This looks like it might be hitting right at 4. Well, let's just check that. Okay, so you could look at the graph, you could look at a table, and again, what I want to do is identify it. Oh, look, there it is. Okay, 4, 0. Okay, now, quick note here. If I use a graph, then I need to sketch the graph. Okay, if I use the table, I need a chunk of table. Okay, so like for instance, if I'm gonna, if I do this by finding a 0 at 4 by using the graph, then I need that. Okay, if I find the 0 by using the table, then I need at least a couple of rows from the table so I can identify what happened to get that. All right, hang on, there we go, this will work. All right, so like at 3, -2. All right, so I just want you to know what I'm expecting to see. So one of the zeros I found by actually looking on the graph, okay? That tells me two things. First of all, I'm trying to find the zeros. So 1, 0 is x equals 4. This is a cubic. There should be 3 zeros altogether. Okay. I found that first 0 either by looking at a graph or by looking at a table, and I need a couple of values from the table or I need a sketch of the graph. Don't spend your life on it. All I'm talking about is a very rough sketch, just like what you see here on the screen. For this sketch is great. This little chunk of table is great. Just a couple of rows, a couple of the consecutive entries in the table is fine. Okay, so this tells me two things. It tells me a 0, and it also tells me a factor. if x equals 4 is a 0, then x minus 4 must be a factor. In other words, if I divide, I should get a remainder of 0 if I use that factor x minus 4. Okay, so watch this. I'm doing the opposite to get to the factor, and then when I divide with synthetic division, if I'm dividing by x minus 4, I have to do the opposite again. A positive 4 goes here. So in essence, the 0 itself could go straight into the box. Now you're going to have to pause this, rewind this, or whatever, and go through that logic a couple more times because I need you to own that. People get real confused. Is this supposed to be a negative 4 or a positive 4? And it's going to be a positive 4 this time because to go from the 0 to the factor, it's opposite, and then to go from the factor into the division, it's opposite. Now you can do long division here if you want. I'm going to do synthetic. So bring down the 1, multiply, add, multiply, add, multiply, add. Now, according to what I said, if x equals 4 is a 0, then x minus 4 should be a factor, and if it is a factor, then the remainder better be equal to 0, and it is. If it doesn't come out to be 0, then something is wrong. Okay, so let's just establish what we just figured out. We know that x cubed minus 6x squared plus 7x plus 4 is equal to x minus 4 times x squared minus 2x minus 1. And I want all of this to equal 0. Well, this equals 0. This whole thing equals 0 when x is 4, but there are two more solutions from this factor. So the question is, can we factor it some more? Now, if I can factor it some more, then that would be sweet. So like x and x, the signs have to be different. Factors of 1 are 1 and 1, but that's not going to give me a minus 2x. This actually doesn't factor. So the question is, how can we solve this? Well, this is going to feel like the never-ending problem until you've done a few of these. And then you'll know that, yes, it is in fact the never-ending problem, but it's really not that big a deal. So we use synthetic division to get this, and now what we're going to do is take this, which is called the depressed polynomial, because we squeezed one of the factors out of it. We depressed it. And we're going to take that little guy, x squared minus 2x minus 1, and set it equal to 0 and solve it. Now again, if we could factor this, it would be easier. We can't. So I'm going back to, your favorite. Opposite of b plus or minus b squared minus 4ac all over 2a. Okay, so this is kind of how it looks when it's ugly. No offense. This is going to be 4 plus 4. Okay, you look at the signs, you figure out why it's plus. 2 plus or minus the square root of 8. Also known as 2 plus or minus 2 root 2. Okay, 8 is 4 times 2. Okay, you can play around with that. And now since every term can be divided by 2, I can make this 1 plus or minus the square root of 2. Okay, now just a quick little recap. This was a cubic. I'm supposed to have how many solutions, how many zeros? Well, there's supposed to be 3. Well, I'm only seeing 2 here, one from the plus and one from the minus, but remember, we also had x equals 4 from the very beginning. So there are 3 solutions. That's how many I expect. This problem is done. Okay, now, I know some of you are tired, and so you're going to stop now, and I'm telling you, that's fine with me. We're going to do one more example of this. I'm going to do one more example. So if you're with me here and you're feeling confident about this, then you can stop now at the 19-minute and 27-second mark. And if you want to hang with me for one more example, then that sounds like a good plan to me. Okay? All right, so one more example. Now this one is 4th degree, which means what we're going to have to do is synthetic division twice. And again, it doesn't have to be synthetic division, it can be long division. We're going to do synthetic division twice. Once we'll take it from a 4th degree to a 3rd degree, Then we'll take that third degree, do it again to get it to a second degree, and then we can do like quadratic formula or some other method, okay? Okay, so again, what we're going to do is do some division. Oh, can't take it all at once. All right, then we'll just leave it. Okay, we're going to do some division, and the issue is, what do we divide by? What are we going to put in the box? So 1, -1. And again, what we're going to do now, back in the dark ages when I was in high school in the early 80s, before graphing calculators were invented, abacus was pretty much done though. We were using regular calculators. We would actually do synthetic division repeatedly, guessing factors. In this case, we would use factors of 10, so 1, 2, 5, or 10, positive or negative, and keep trying until we got a remainder of 0. And then there are some other things you can do, but honestly, it's so much easier with the calculator now. So I already put the equation in. I'm going to hit graph, and it seems apparent that, well, it's crossing in 4 spots, so there are definitely 4 real zeros. It's just a question of which, what are they really? Now it looks like maybe -1. So let me go to the table and just see. So -1, 0 is one of the solutions. Sorry. Okay, so -1, 0 is a 0. Okay, and again, our graph, let me just pop back for a second to get a rough idea of what it looks like, because we need to sketch it. All right, looks like a W, but it's low on the left side. Okay, so something like that. Okay, so -1 is a solution. That I know. Okay, so we're solving. So I'm doing synthetic division. Bring the first number down. Multiply, add, multiply, add, multiply, add, multiply, add. Cool. I need the remainder to be 0 for this process. Now, I don't want you to assume that the remainder is always 0 for every synthetic division. That's obviously not the case. Okay. Now, that's great. That's one of the zeros. Now, I need another 0, because the other factor comes from it. So let me go back to the table and see if I can find anything. 2. 2! Awesome. All right, so 2 is a 0. Okay, so we got 1 at -1. The other one is x equals 2. So what we're going to do is do a whole nother synthetic division, just picking up right where we left off, because this guy right here is the cubic. This was 4th degree, this is 3rd degree, and now if we keep going, what we're left with after that will be 2nd degree. Okay, so bring down the 1, multiply, add, multiply, add, multiply, add. Remainder is 0. Woohoo, I needed that. Okay, so ultimately what this is now is x squared plus 0x minus 5. I need this to equal 0. Well, this one, because there's no b term, the b is 0, I can actually just add 5 to both sides, and then I could take a square root of both sides. So when I take the square root of each side, this ends up, the absolute value of x equals square root of 5. So in other words, x equals plus or minus the square root of 5. Now remember, this was really 4th degree. So there are 4 solutions, supposedly. Okay, well, one of them was the x equals -1, one of them was x equals 2, and the others are this plus or minus square root of 5. So I'm going to write those all together. Okay, so the zeros are x equals -1, x equals 2, or x equals square root of 5, or negative square root of 5. Okay, and that really is it. Now again, this is a big process. You need to be patient with yourself, but the idea is find all of the solutions. Okay? All right, well, thanks for watching. It was still under 25 minutes. I know that some would call that a TV program, but again, this was just one more example. I think it's a good one, though. Thanks for watching. Bye.